Guys, I'm going to be going through some of the odd problems here. So for question 1, they give us a couple of limits up there. And the directions say the table above gives selected limits of the functions f and g. What is the limit of this expression? And they just want to verify that you do understand the properties of limits. So basically, if you're taking the limit of an expression, you can just apply the limit to each thing that's being added. Constants can be taken out of the limits. Now, the limit of g of x as x approaches 5 is apparently equal to 5. So this is basically just 3 times 5. This one here is a little tricky. I've never seen something like that, but as you'll notice, the x is negative. We don't have the limit of f of x as x approaches 5 with a negative on the side. We have it with a positive. But you guys can imagine if I were to plug 5 in there, it's just going to become negative 5, right? So this is the same thing as this. Because if I plug 5 in, the 5 just becomes negative. So that's like I'm plugging in a negative 5 to the regular f function. And they tell me that that value there is apparently 4. So we have 4 plus 15, which is 19, would be the final answer there. So take a look at question 3. I'll leave question 2 for you. All right. So this is a L'Hopital question, probably. I already see that if I were to plug in 0, when you're doing limits, by the way, you always start by plugging 0 in. You plug your number in first. I'm just going to get 0 over 0. That's a L'Hopital situation. So we would take the derivative of the expression, which is 12x to the 5th plus 18x squared over 20x to the 4th plus 9x squared. Now, if I plug in 0 to this, I'm still going to get a L'Hopital situation. Still going to be 0 over 0. I got to keep doing that until it doesn't occur anymore. So if I take the derivative again, that would be 60x to the 4th plus 36x over 80x cubed plus 18x. Still would get 0 over 0 if I plugged in 0. So I'm going to do a derivative again. 240x plus 36 over 240x plus 18. And now this time if I plug in 0 over 0, only these pieces go away, and I'm left with 36 over 18, which is 2. Okay. Go ahead and move on to number 5. So that's L'Hopital, and you guys will use L'Hopital to work on number 4 as well. So this is kind of an interesting question. They start off by telling us what this limit is equal to. It's equal to 1. And then they ask us to find this one. And so what that means is somehow we're going to have to mess with the way that this thing looks so that we get something like that in there so we can plug the 1 in. Okay, so I'm going to show you how to do that. First of all, we're going to use our trig identities. Cotangent can be rewritten as cosine over sine. Okay. Next, I'm going to multiply the top and the bottom of this fraction by sine 2x. So that this cancels out. All right, so remember my goal here was I wanted to somehow get this. Well, as you can see on the top, I want a sine 2x, and now I've got that on the top. And on the bottom, I want a 2x. So that can be achieved pretty easily here. If I can just rewrite the 8x, I can make that a 2x times 4. Isn't that the same thing? So now what I can do is I can think of this as sine 2x times cosine 5x over 2x times 4 cosine 2x. We're taking the limit of this as x approaches 0. Now, the limit can apply to this and this separately, so we'll do the limit as x approaches 0 of this piece multiplied by the limit as x approaches 0 of our other piece. This, they tell us in the beginning, is 1, so that's why they gave us that. As for this one, we can just do direct substitution. If you plug in 0, you get cosine of 0. Cosine of 0 is 1. And cosine of 0 on the bottom still gives me 1. So I end up with 1 times 1 over 4 times 1, which is 1/4. Okay? And that would be that one. So the idea there is to rewrite this using trig identities and just moving some things around until you get this. And then from there, you should be able to do some direct substitution and find the limit like normal. Yeah, so I never gave you one like that when we did trig limits, but we've gone over all those concepts like trig identities and separating limits. It's just we never did it with that kind of a problem. All right, so that's yours. Let's go ahead and take a look at number 7. Now, whenever you're trying to find the limit of a rational expression that has square roots in the numerator or the denominator, we use a strategy called rationalizing. It's been a while since we've done it, so let's review how to do that. I want to find the limit as x approaches 2 of x squared minus 4 over the square root of x minus the square root of 2. Well, the process of rationalizing goes like this. You're going to multiply the part that has the square roots by itself, but with one little difference. It's going to be opposite sign. So since it was originally negative, I'm going to put a plus there. And whatever you do to the bottom, you're also going to do to the top. Okay? And when you do that, first of all, in this case, the top is, I'm not going to actually multiply anything together on the top. I'm just going to leave them separate. But on the bottom, we are going to multiply. And since these are what we call conjugates, all you have to do is do the first two multiplied together, which is x, and the last two multiplied together, which is 2. And there's our answer. Now, typically at this point, what you would do is you would remove the discontinuity, but I can't cross anything off yet. But hopefully you guys recognize that this is a difference of squares, so we can actually factor that. X squared minus 4 is x minus 2, x plus 2. And now that I've done that, we can remove the discontinuity, and I'm left with this. Now the next step would be to plug in the 2, but I already looked at my multiple choice, and I already see this expression over there, so that's the one that they want. Okay, so they just wanted you to remove the discontinuity, not actually finish the limit. Okay, and so you'll have one where you need to rationalize. For this one, though, they actually want you to go ahead and find the limit all the way by plugging in the number. All right, let's go ahead and move on to our next one here. All right, so for this one, we're being asked to find the limit of this function as x approaches 2, and this is the function we're working with. Notice it's a piecewise function. When we find limits of piecewise functions that are written like this, where it says x equals 2, it's pi, but for all other x's that aren't equal to 2, we're going to use this. Well, back when we did that, I told you guys to rewrite these. So this is the first thing I want to remind you of. The one where it tells you what it is at x equals 2 goes in the middle. And for all other values of x, it's the other function, which means that for x less than 2 and for x greater than 2, we're using this guy. Okay, now here's the problem. When you're doing a limit of a piecewise function, then what you need to do is you need to find the limit as x approaches 2 from the left, and you also need to find the limit as x approaches 2 from the right. And if those two things match up, then that's your answer. If they don't match up, then you have no answer. Okay? So the problem here, though, is that to find the limit of f as x approaches 2 from the left, we would be using where x is less than 2. We would be using this function. Okay? And for the one on the right, we'd be using the same function. Now you might think, well, therefore they're going to come out to be the same, right? Well, maybe not. There's a little bit of a problem. First of all, you can't plug 2 into these. They have a discontinuity. If you were to plug 2 in, it makes the bottom equal 0, which is not allowed. Okay? So right now, I'm not really safe to find these limits yet. I have to do something else. And this is the other big thing that I wanted to remind you of with this problem. So the first big thing was how to rewrite this. Another big thing I wanted you guys to know was finding limits from the left and right. That's how you do limits on piecewise functions. Now, here's the third big thing I want you guys to know how to do. I want you to know how to change a piecewise function into, an absolute value function into a piecewise function. So, right now, we're dealing with the expression x minus 2 is an absolute value expression, right? Well, we said before the cusp happens when x minus 2 equals 0. And so the cusp happens at 2. And then what we did was we did a little number line test. And all we did was we plugged in numbers to see what happens to the left of 2 and to the right of 2. So if I were to plug in a number less than 2 here, like let's say I plugged in 1, does a change of signs occur? Yes. Which means that if I plug in a number bigger than 2, there won't be a change of signs. And what that means is I'm going to come over here to my absolute value expression, and I'm going to replace, for the x less than 2, I'm going to replace that with just x minus 2, but with a changed sign, because for x less than 2, the sign changes. Whereas for x is greater than 2, there is no change. So it's just going to be x minus 2. So I'm going to get rid of those. That's my first thing I need to do. The next thing I'm going to do now is notice that this x minus 2 can cross off x minus 2 there. Okay? Now this is getting to be pretty messy at this point. So I'm going to write what we have so far at this point in time. Okay? Right now I've got x minus 2 times sine x over negative 1. Then I have pi. And then I have x minus 2 times sine x. And you can just put a positive 1 there if you want to. This is less than 2. This is equal to 2. This is greater than 2. So I've had to do a lot of stuff here with this expression to rewrite it. But now that I've done that, now that I've rewritten it and removed the discontinuity, now I can finally answer the question, what is the limit? And once again, we do that by taking the limit from the left, and we take the limit from the right. And now I can actually do that because I've removed the discontinuity. So if I were to plug in 2, I get 2 minus 2 times sine of 2 over -1, and 2 minus 2 times sine of 2 over +1. This, from the left, we plug it into the top piece. For the right, we plug it into the bottom piece. Now, as you can see, this one's a -1, this is a +1, so it makes it kind of look like they're different, but be careful. 2 minus 2 is 0. And so both of these just come out to be 0, and therefore they are the same, and therefore that is the limit. So there's a lot of great stuff in this problem to review. Okay, let me review the big takeaways I'd like you to have from this. First of all, it's this situation. We want to rewrite those into this. That's one big takeaway that I'd like you guys to have. All right. Another big takeaway that I'd like you guys to have from this problem is how to change an absolute value function using that number line thingy. Okay. The third big takeaway I'd like you to have from this is that the way that you find the limit of a piecewise function is you have to do the limit from the left and you have to do the limit from the right. Now, this problem is a hard problem because it has 3 big ideas in it that are hard to remember. But what's important about reviewing this right now is the fact that each one of these ideas is important, and just because this problem is hard doesn't mean that going through it isn't going to be helpful for some more simple questions that might have only one of those important parts to it. So it's a cool problem to review a lot of stuff. Nevertheless, it is kind of a pain in the butt because there's a lot going on there. But here's one for you guys, quite similar. I wouldn't make the assumption that it's just going to come out to be 0 again, although it might. I don't know. I haven't solved it. But I'll leave it to you, okay? All right, let's go ahead and take a look at question 11 here. Let's shrink this up a bit. All right. So in this problem, they're giving me 3 representations of a function. They give me a piecewise function. They give me a table. And they give me a graph. Currently, they're asking me which of these representations can be the function g of x provided that the limit of g of x is 5 as x approaches 1. All right, well, the table and the graph are pretty easy to see. Number 1 is a piecewise function, and we're going to use one of those big ideas that we reviewed on the last set to help us answer it. But for now, let's start with the easy stuff. As x approaches 1 from the left and from the right, g of x is approaching nothing. Okay? G of x is getting bigger and bigger and bigger and bigger. Okay? So what's happening is, on this graph, is even though g of x is equal to 5 at 1, the graph is shooting up into infinity as it approaches 1. On this side, it's approaching negative infinity. So even though the function does exist at 1, the function is 5. Since the left and right-handed limits are not meeting up at 5, this cannot be the function g of x because the table does not give us a function whose limit is 5. The function equals 5, but its limit does not. This limit does not exist. So it can't possibly be this one. All right? Now let's take a look at number 3. On number 3, the limit as x approaches 1 from the left and right is 5. That's correct. We are approaching the y value 5 as I get closer and closer to that spot. And so, yes, this can be 3. That's a good one. Yes? No. All right, I'm going to have to erase, but we'll remember that. Let's go ahead and check out number 1, though. Now, one of our big ideas I share with you is that we like to rewrite this whenever they write it like that. We like to do less than 1, greater than 1, equal to 1. Sorry, I have to squish all this in there, but hopefully you guys know what I'm writing there, just from the original problem. All right, and another big idea that we have to use is we have to show that to find the limit of the piecewise function, we do the limit from the left, and we do the limit from the right, and see what we get. All right, so I'm going to plug 1 into this function, and we'll see what we get. This is from the left. Oops. Unfortunately, I get 0 over 0. Now, that doesn't mean there's no limit. That just means I need to do L'Hopital. So let's do L'Hopital. If I take the derivative of the top and bottom, I get 2x plus 3 over 1. And now we'll do the limit as x approaches 1. So plugging 1 in here, I get 2 times 1 plus 3, which is 5. Now, this function is exactly the same. So when I take the limit from the right, I'm using the same exact function, and I will get the same exact answer, and therefore that will be my limit. The limit is 5, which is what it's supposed to be. So yes, once again, the top one is another answer. So what we found then is that both 1 and 3 are possible representations of this limit. Okay, so for 3, you could just look at it, right, for graphs. For the table, you have to see, is the y value approaching a specific limit or not? For this guy, you need to rewrite it and actually find the limit. Whichever ones give you that limit value are possible representations, and you do have one like that for yourselves here. So I'll let you guys try that one. So this problem is reviewing for us something known as the squeeze theorem. I didn't teach this lesson, but I did offer it as an extra credit thing. Some of you guys might have did it, some of you may have not. I'm going to put it in here because it's really not all that complicated, and we'll just let you guys practice it, because you probably would see maybe 1 or 2 questions like this on your AP exam. They're just not a huge deal, though. So first of all, they give me 2 functions, g and h, and then they talk about this other function, f, and apparently f is always in between g and h for all values of x between -1 and 2. Now, they want to know what's the limit of f of x as x approaches 1. Well, here's the thing. If f is always between these 2 things, let's say that g is equal to 5 and h is equal to 5. What would f be if it's always between them? Well, it would have to be 5, right? So that's just an example of the squeeze theorem. If the left-hand side and the right-hand side are the same, then the middle one must also be that. So if f is between g and h, then that means that the limit of f must also be between the limits of g and h as x approaches 1. So why are we doing this? Well, I can't find the limit of f because I don't even know what the function f is. But I can find the limit of h, and I can also find the limit of g. And if it turns out they're the same thing, then that means that this would have to be that value also, since it always has to be between them. All right? And I just recognize this problem because it's a very typical, common problem, and that's how you'll notice it. And if I'd never seen the squeeze theorem before, I might have looked at this and thought, well, what if they're not the same? Well, then that's what option D is for. You just wouldn't have enough information. But I'm pretty sure it's going to work out. It usually does. So let's go ahead and do that. We're going to plug in 1 to the g function, which means we have sine of pi over 2, which is 1, and 1 plus 4 is 5. Now we'll plug 1 into this function. So 1 cubed is 1, and so we have -1/4. Plug 1 in here, you get 3/4. and then 9/2. All right. Well, negative 1/4 and positive 3/4 makes 2/4. 2/4.
Attention, staff and students. They are testing the alarm, so if the fire alarm goes off,
Sorry, the announcement's on.
evacuate.
2/4 reduces to 1/2, and 1/2 plus 9/2 is 10/2, which is 5. And sure enough, just like I thought, and that's also another funny coincidence. I didn't know these were going to come out to be 5, but when I did that example earlier, that was just chance. Kind of funny. But anyway, since both of these are 5, that means this has to be 5, and that would be our limit. That's called the squeeze theorem. So whenever you see this little thing where they show 3 functions in order like that, that's probably what you're going to be working with, the squeeze theorem. And so you'll have one like that here. All right, let's go ahead and take a look at question 15. The graph of the function f is shown above. What are the values of x for which f has a removable discontinuity? Removable discontinuities are continuities where the limit exists, even though there's still a discontinuity. Now, there's only 2 ways that can happen. One way that could happen is if you have a hole. The other way that can happen is if you have a hole with a dot below it. But those are the only types of removable discontinuities exist. In both of those cases, the limit exists because the lines connect at a common point. And so we only have I see 2 places where this occurs. I have one here, and we have one here. And so they want to know what are the values of x for which it has a removable discontinuity. Well, that looks like it would be x equals 0 and x equals 2. And so there you have it. Number 16 is similar to that, so I'll let you guys do that one. Number 17, let f be the function defined by this. Which of the following statements is true? I really don't like these questions because instead of solving it and then finding your answer, you actually have to read each option and try to figure out what direction they're trying to get you to go in. So let's read our options. Option 1, f has a discontinuity due to a vertical asymptote at x equals 0 and x equals 4. Another option is x has a removable discontinuity at x equals 0 and a jump discontinuity at x equals 4. F has a removable discontinuity at 0 and a discontinuity due to a vertical asymptote at x equals 4. And then finally, f is continuous at 0 and f has a discontinuity due to a vertical asymptote at x equals 4. All right, well, a discontinuity is going to happen anytime the denominator is equal to 0. Okay, so let's go ahead and start by factoring these expressions here. First of all, on the top, I can take out an x squared. And on the bottom, I can take out an x squared. I also see that this on the top is a difference of squares. All right, well, anytime the denominator is equal to 0, you have a discontinuity. So we have discontinuities when x squared equals 0 and when x minus 4 equals 0. So that means we have 0 and 4. And that's not surprising because those are all the options they were talking about over here. Now the question is, what kinds of discontinuities are they? Well, on an equation, if you can cross that thing off from the top and the bottom, then that's a removable discontinuity. So x equals 0 is a removable discontinuity. But the x equals 4 does not cancel. So that's a non-removable discontinuity. So we have a removable discontinuity at 0 and a non-removable discontinuity at 4. Now we mentioned earlier that a removable discontinuity is like a hole. Non-removables can be either a jump or they could be a vertical asymptote. Okay? Now jumps only happen with two types of functions. They only happen with absolute value functions or piecewise functions. And this is neither one of those, so I'm not going to consider that. So what this means then is this function has a hole at 0 and an asymptote at 4. So now let's revisit our options here. F has a discontinuity due to a vertical asymptote at 0 and 4. Well, this isn't true because at 0 we don't have a vertical asymptote, we have a hole, so that one's false. Part B, F has a removable discontinuity at 0, that's true, and a jump discontinuity at 4. That's not true. Only absolute value functions and piecewise functions have jump discontinuities, so that's no good. Part C, F has a removable discontinuity at 0, that's true, and a discontinuity due to a vertical asymptote at 4. And there's our winner. Okay. Part D, F is not continuous at 0. It has a removable discontinuity at 0, but it's not continuous. All right, so that one's dead as well, but we already know the answer is C. All right, and so I'll leave you guys to do something similar here with exercise 18, and that'll be it for the day. So hopefully that was helpful, and we'll see you guys in class.